All right, so the last talk will be by Derek Murray. This is the subtitle of your incremental iterative.
It is, yeah.
Okay, so 3 I's, incremental, iterative, and something else.
Interactive.
Interactive and analytics.
But more simply, it's going to be about a system called Naiad. So thanks very much for the introduction. Good afternoon, everyone. My name is Derek Murray. I work at Microsoft Research Silicon Valley. And there, we're building a system called Naiad that I'm going to tell you about today. So Naiad is a general-purpose system for large-scale distributed analytics. It includes support for graph algorithms and machine learning. But wait a minute, we're at the Graphlab workshop. So why am I up here telling you about a computing system? Computing system makes sense. So I'm really gratified that about 2 or 3 talks have included a slide that looks very much like this, because what I want to do today is revisit the trade-off between data parallel systems, those like MapReduce, and graph parallel systems, those like Pragle and Graphlab. So remember from Carlos's keynote this morning that many algorithms on graph-structured data are better suited to running on a graph parallel system. But those systems have a more constrained programming model that limits how widely they can be, among how many problems they can be applied. So to see the difference between the two, let's start with the kind of data that they can process. On the data parallel side, MapReduce is tremendously successful because it's so omnivorous. There's no schema, no structure. You can just dump text into HDFS, and Hadoop will lap it up. The graph parallel systems, though, as their name implies, are specialized for graph-structured data. Now, if your data are already in that form, sorry, is there a problem? I think it's the platform. Can we turn down the level a wee bit, and then I can lead in.
I think the microphone's in the laptop. Is the microphone?
No.
So this is station. Can you wiggle?
Is that a little better? It's going to turn into a dance party here, folks. I'm sorry.
Don't breathe and we'll be
Okay, it's only 15 minutes. I can hold my breath. Where was I? Yes, graph parallel systems are specialized for graph-structured data. So if you've already got your data in that form, you're in luck. But sometimes you have to extract that structure yourself. Be that from crawler logs, from social network fire hoses. Maybe you've just got your hands on a tranche of cell phone metadata. But in that case, you can use things like Graphlab 3 and Graph Builder, which Ted talked about at the beginning of this session, to get around this limitation on the ETL side. There are also times, however, when you need to support non-graphical data at intermediate stages or for producing human-readable results. And that's when a more general-purpose system is useful. What about programmability? Well, MapReduce and its cousins really took off when they got support for building complex workflows. Because a MapReduce job is just a function that turns one data set into another. You can use your favorite domain-specific language to build complex workflows out of these jobs. So as a C# programmer, I'm quite partial to using LINQ to do this, but there are Hive and Pig and many others that allow you to do this on Hadoop. The graph parallel systems ask you to think like a vertex, but if you have to think like a vertex, poor little vertex can only be expected to think so much. You're limited to having a single vertex program in which all of your parallel logic is bundled up. And it's hard, if not impossible, to implement your whole data processing pipeline in a graph parallel system. Things like the warp graph stuff we saw this morning are getting towards a more all-in-one solution, and so is Graph Builder. But if you're having to write vertex programs, you're kind of restricted to writing parallel computations on the graph. So the existing data parallel systems are let down by their poor support for iteration. They're designed to scale to huge distributed data sets, and so they sacrifice support for fine-grained state updates in order to process huge batches of records at the highest possible throughput. The key benefit that a graph parallel system adds is first-class support for rapid iteration while relatively small changes are being made to the graph state. The bottom line here is that the two classes of system have historically been good for two very different things, but today I'm going to tell you how Naiad lets you have the best of both worlds. Now, in this talk, I don't have time to go into the algorithms and the implementation details that make the system tick, but I do want to outline the 3 key features that allow Naiad to deliver the performance of a specialized graph parallel system with the flexibility and the programmability of a data parallel system. And then I'll give you a taste of the results the system can achieve. So the first and the most important feature for getting low latency in Naiad is incremental operators. So a Naiad program is built up by connecting together data parallel operators. Think of these like the map and the reduce phases in a MapReduce program, but extended to support things like joins between two data sets. For example, we might, as we have here, have an operator that groups records by key and emits the minimum value in each group. To achieve parallelism, we divide the records into shards, where each shard does all of the processing for its partition of the data, here according to the first letter of the key, and as they arrive, the shard updates its state with the minimum value. So in Hadoop, once all of these, if you did something like this in Hadoop with a reducer, once all these records are collected, they're written out to HDFS and then discarded from memory. This means that when a new record for Alice comes along, it has to process the entire data set again. So the idea in Naiad is very simple. We borrowed the old idea from incremental view maintenance in relational databases. We keep the state of the output and some additional metadata in memory across the shards. And that way, when new data arrive, it only does work proportional to the size of the change. Moreover, all of these operators are designed to exchange differences rather than whole data sets. So when only a few records change, the amount of data exchanged is much smaller. We've implemented a broad set of operators in this context, including the standard select, where, join, group by, and aggregate that you will be familiar from SQL. Depending on the use case, there are simple versions that allow append-only data, and also more sophisticated ones that allow you to delete records at the expense of keeping a little more state. But all of them allow you to plug in user-defined functions, so you can handle unstructured data, just like in MapReduce. Now, in a data parallel framework, many graph algorithms have a similar shape. You start with a graph, defined as a set of edges, and the current value of each vertex's state. A join allows each vertex to broadcast its state to all of its neighbors, and a group by vertex ID allows each vertex to compute a new state based on the states of its neighbors. In fact, the join and the group by are just like the scatter and gather steps in Graphlab's gas abstraction. Now, you can write these two steps as a Hive or a pig program, but these don't support iteration. What Naiad adds is the ability to feed back operator outputs using structured cycles in the data flow graph. And the reason using a cycle rather than unfolding the graph is useful is because these join and group by operators are incremental. Only the vertices that change from one iteration to the next need to be communicated. And that means that this loop is able to iterate rapidly when the changes are sparse, just like in a graph parallel system. We've implemented iteration in a general framework called differential data flow. This supports efficient iteration and also allows you to have loops that have incrementally updated inputs. So we will maintain the state of an iterative computation and allow, well, I promise that wasn't me that time. And it will allow you to change the input, producing the correct answers to the iterative computation as it goes along. This enables Naiad to do things like compute sliding windows over iterative algorithms. And these algorithms may even contain nested loops and other ordering constructs, such as prioritization, which is useful for asynchronous algorithms. So how do you actually write one of these programs? Well, the current version of Naiad is implemented in C#, and it supports a declarative programming model based on link. The first thing to note is that all the records are strongly typed .NET objects. So defining these types up front allows us to automatically generate all of the serialization code so that Naiad runs seamlessly and efficiently on a cluster just as well as it does on a shared memory machine. It also allows the programmer to use standard IDE features like IntelliSense autocomplete. All Naiad programs are defined in terms of incremental collections. These are typed collections of records that allow the programmer to supply records incrementally using an observer pattern. And now here's how you might write a graph algorithm in Naiad. The particular details of this algorithm aren't important. In fact, what it's doing is computing the weakly connected components of a symmetric graph using the hash min algorithm that was just described in the last talk. But the main thing to note here is this fixed point operator that builds a cycle in the graph, the data flow graph, and iteratively applies the join, concat, and min operators to the input collection. And because this is slideware, I don't have the space to build up a complex workflow, but the definition of edges could be replaced with some more complex ETL workflow. Any arbitrary C# code can be put there, including parsing, filtering, and partitioning, or even a separate iterative computation if you want to do some graph coloring-based partitioning. And the result of the fixed point is just another collection of records. It's a multi-set of records which could be subjected to further statistical analysis that doesn't necessarily need to respect the structure of the graph. Although we like to use link because it has nice composable semantics, we understand that it's not for everyone. And so it's possible to define other domain-specific languages on top of the system. For example, and just like everyone else, we've implemented a version of Pragle that on Naiad, and ours supports the full Pragle API, including graph mutation. And these DSLs are implemented on top of a low-level Naiad API that allows you to define and wire together data flow vertices. Currently, we're investigating what other languages can be built on top of this. And if you have a particular favorite language that you'd like to see, please speak to me afterwards. I'd be interested to talk about that. Well, so far, I've dealt mostly in abstractions. But before I go today, I want to give you an idea of how the system performs. We've implemented a version of Naiad that runs on modestly sized clusters of up to 64 machines. And here I'm going to show the running time of a PageRank iteration on the Twitter follower network graph that has turned up as well in a few talks already today. This is about 41 million vertices and 1.4 billion edges. And it's an example of the kind of natural graph that's historically been difficult to process in a distributed system. On the x-axis, we have the number of machines, and on the y-axis, the time per iteration, so lower is better. And note that it's a log-log scale in this graph. So for comparison, we took the results from Paragraph, and these are the results from the OSDI paper, which uses the gas abstraction to get efficient results in this problem. Now, these are old results. Yu Cheng and Joey were kind enough to send us the updated ones just 2 nights ago. And they told us that on 64 machines, it's now up to running at about 1.8 seconds per iteration, so a really impressive speed up there. How does Naiad compare to that? Well, on 64 of our own 8-core machines, they're slightly more elderly and the network's a little slower than the EC2 cluster that was used for the Paragraph experiments. An iteration of PageRank takes just under half a second. Now, we heavily optimized the Naiad network stack to perform overlapped computation and communication, and optimized the data layout for cache locality. But the main point to take away from this is not that this is an extremely fast way to do PageRank, but more that a general purpose framework can deliver performance that is competitive with a specialized framework like Paragraph. I also want to give you a taste of some of the other things that Naiad can do. So for example, we've looked at some streaming algorithms on the Twitter mention graph. And that's, as we heard, I think, a couple of talks ago, the graph formed by the @mentions and retweets in the Twitter firehose. So Naiad can compute a 24-hour sliding window of the connected components in that graph and maintain it in real time with 50 millisecond latency. Now, connected components are all very well, but in a network like Twitter, they lose information about the direction of communication. So for example, if I tweet at Justin Bieber, that doesn't say very much about the mutual connection between us. But if I tweet at him, he gets retweeted by Lady Gaga, she tweets at President Obama, and then he tweets back to me, there's much stronger evidence that I am part of a high-powered celebrity cabal. And strongly connected components is an algorithm for finding just such cabals. It's more complicated than the undirected algorithm, but now I can also compute these on the same sliding window, maintaining that in real time with 1 second latency. In fact, this is a neat example of a nested algorithm where weakly connected components is included as a subroutine and applied forwards and backwards on the directed graph to get labels, and then we iteratively throw away edges. I'd love to go into more detail about that, but we're not going to have time. What about non-graph algorithms? So, I mean, I've made a great play about this being a general system. Well, what we did was we ported the logistic regression code from Vaupel Wabbit and used Naiad to implement the all-reduce aggregation step that accumulates a global gradient vector and requires, in our test case on 64 machines, aggregating 51 gigabytes of partial aggregates in each round. Using Naiad to do this led to a 35% improvement in the overall performance and a 3x improvement on the critical path, which gives us some idea that the system is quite good for shoveling around large amounts of data, as well as fine-grained updates. Now, for me, the exciting things about these examples is that they all fit in the same system. So it's trivial to combine the results of more than one computation in the same job. In fact, the support for sliding windows makes it straightforward to build tools that interactively explore historical data while using incremental graph analysis to reduce the data down to a manageable size. So I'm just about out of time, or I'm just about out of the time that I was planning to take, so we'll get to coffee soon. So to conclude, in this talk, I've introduced Naiad, which is a general data parallel system, combining the performance of specialized graph parallel frameworks with the flexibility of generic data parallel frameworks. And what's more, by giving you the ability to implement your whole computation in Naiad, you can take advantage of the automatic incrementalization it supports, which creates new opportunities for real-time incremental and historical analysis. There's a lot more information on our website here, and we invite you to download the code and try it out for yourself. So you can get the code for the whole system. As I said, it's written in C#, but it runs on Windows, Linux, and Mac OS using the .NET CLR or Mono as appropriate. And if you have any questions, feel free to send the team an email or a tweet. So at this point, I'd like to thank you all for listening. I don't know if we have time for questions, but I'd be glad to take them.